In this video, we're going to go through an overview of buckling of members in compression. This is really going to focus on columns and really how sort of the background of how we design compression members, particularly for steel columns, and how to deal with that buckling force. But before we sort of dive in and start looking at derivations and the mathematics, let's just give you a little bit of a roadmap of where we're going with the lecture. So the first thing is that we're going to look at the global buckling behavior of an elastic Pinpin column, and that's just really going to be a review of Euler buckling. Kind of what we're going to do there is we're going to look from the moment curvature relationship that we see from our free body diagram. So this is looking at the relationship between the moment and the curvature, but we can relate curvature to deformation, and then from there we'll solve the differential equations which get generated from that, and then we'll essentially derive this critical buckling load NCR equals pi squared EI, so the modulus of elasticity times the second moment of area, so moment of inertia, divided by the length of that element squared. Then we'll go through and we'll look at how we deal with other support conditions and really how we're going to change this length in order to essentially use an effective length so that we can deal with end conditions which are different from just pin, and so we can look at fixed pin, cantilever, etc. But with this whole global buckling derivation that we'll look at, that's really focused on what are essentially these elastic and rather idealized loading conditions where all the loading is concentric. So we'll look at basically if we have some eccentricity in the column, whether the column itself has some deviation of straightness along its length, or if, by the way that we load it, we might have an eccentric load coming in. So, this eccentric load is quite common when we look at beam column connections. After we do that, then we figure out, well, how do we, all of this has just been looking at an elastic section, but, real materials yield. And so we need to figure out, well, how do we incorporate that that yielding in our derivation and our eventual design equations. And so we essentially what we want to do is go from a critical load to a critical stress, and that's sort of the overview of where we're going with this lecture. So with that, let's hop in and have a look at really this first part, which is going to be our derivation of the global buckling and the force of this sort of critical force which is required in order to get some column to buckle. So that's what we're going to start with. So looking at kind of our background theory. What we'll see is that if we want, so say that we've got some member. It's a simply supported member. We'll just draw it like this, and it has a roller at one end, and from that roller we're going to put some load N, and based upon as we push on this element, it's going to want to buckle. And so if we then look at that deflected shape will look something like what's drawn here in red. And so let's put some let's make sure that this is in equilibrium for us here. So if we have some value n, well, let's draw a free body diagram of this state, and let me give you some coordinates. So if we go over to the right, this is going to be the z direction, and then the amount which we have deformed and how much we've buckled out from this original plane, we're going to call that value v. So if we draw our free body diagram here, what we get is if this is our essentially our undeformed shape, and then the red is the buckled shape. Well, there's some force N here at the top. Like I said, this distance here is V. This distance here is Z. And then if we'll draw it in red, we'll draw what the internal forces are. So we'll have some axial load. We'll have some shear. There'll be some reaction shear up here, shear, and we have some moment M. So if we take our moment, so if we sum our moment about this point Z, and we set that equal to 0, we essentially want to solve for what is this value of M. And if we do that sum about this point, well, these two forces are concurrent, so they have no distance. In fact, we'll say that these two are actually going to cancel each other out. And what you get in the absence of any force coming up here is just going to be the moment equals n times this distance v. And that makes sense. The moment which is caused from buckling is really just going to be the where this internal force is acting within the buckled member. So if you think, that if we buckle this member here, we've got force running along the axis. Well, if we buckle it, it's now in a curve, and so you've got you have a component in both the sort of the x and the y direction, which is what we're seeing here. And this sort of the moment that we're looking at is this this moment, which is from the axial direction, and that's just going to be based upon the distance which this buckled shape is from the center line between the two, like I said, between the center line between the 2 points of support. So, well, we know what the value of this moment is, and really what we want to do is get some form of equation which tells us how much this value v will be with respect to the applied load n. And then, in essence, what we want to do is sort of rearrange that and find out, if we have no buckling, well, this v equals 0. So that's just everything's acting in a straight line. So we want to find out, well, what is the value n, which creates some, out of plane movement, some buckling. So if we look, from our moment curvature relationship, and just so that, just for a reminder, that moment curvature relationship is just m equals negative ei times the second derivative of displacement. So if we substitute in this n sub v for m, what we end up with, and I'm just going to swap the sides of the equation here, we're going to end up with negative ei multiplied by the curvature equals n times v. And well, let's just rearrange this a little bit, and let's factor out this EI term. And what we end up with is our curvature plus our axial load n times the displacement out of plane v over EI equals 0. So, well, this is essentially a differential equation, and really what we want to solve is, what's the solution to this equation? What makes it true? So to do that, and to get everything into kind of a nice homogeneous constant coefficients form, we're going to pull a little bit of a trick, a mathematical trick, and we'll just let the value of n over EI equal this constant alpha squared. And this, as I said, is just sort of a mathematical nicety in order to get the differential equation to have nice coefficients here. And so if we do that, then we get the curvature plus alpha squared times v equals 0. And all of that is just a second order differential equation, so diff EQ, and it's a homogeneous differential equation with constant coefficients. So that means in order to find the solution has sort of a form that looks like this, where v sub z, so this is the, just thinking about what this means, this is the out of plane displacement with respect to our distance along the compression member. Well, that just equals a times sine alpha z plus b cosine alpha z. Then if we look at our boundary conditions in order to solve for what these constants are, so, our boundary conditions, we have v of 0 equals 0. So v of 0 is just going to be at the support here. So the out of plane displacement at the support, at a pin support, is 0. So it's sort of by definition of that pin support, it can't translate up and down. And that's essentially just saying no buckling at the support. All right, so that's pretty straightforward. And so if we do that, so v of z is 0, so we can plug all of that in, and we can solve this equation. In fact, we'll box that equation just for reference here. And if we do that, we find that this coefficient b equals 0, because a sine of 0 is 0, 0 times cosine. So that means that this factor has to be 0 in order to make that equation correct. And then, so what we end up with is, let's rewrite this equation now that we know that the coefficient b is 0. So we get v sub z equals a sine alpha. So even though we haven't solved the equation completely yet, we have something which is interesting, and that means that the buckling shape is going to have to be a half sine wave, and that makes sense. I mean, if we grab our little buckled shape here, let me just get you a a column with a reference line here. So if we have this Pinpin at the end, well, and we buckle it, well, that certainly does look a lot like a half sine wave there. And so, that's always nice that the mathematics seems to approximate, what we're seeing in reality. And so, I mean, that's worth even writing down that, the buckled shape will be a 1/2 sine wave. Cool. So we still need to solve for what this coefficient a is. So if we found out that b equals 0, we need to find this coefficient a. And so the only other boundary condition, the only other place where we know what our out of plane deformation is relative to the length is if we go to the total length L. So we saw when z was 0, we were at this support, we knew we had no out of plane movement. When z equals L, we'll be at the other support. We also know that we have no out of plane movement, so v equals 0 at this location as well. So putting that in, we have v of L is going to, that also equals 0. So that gives us a sine of alpha times L equals 0. Sine of alpha L equals 0. So for that to be true, alpha L equals n times pi. And so what this means is we still have this half sine wave, but it's going to be a number of half sine waves will be sort of what all of our buckling modes are going to be, what we call buckling modes. So if we just sort of repeat that up here, just so it's at the top of this page again. So if alpha L equals n times pi, and n equals 0, 1, 2, 3, all the way up to n. Well, that just means that we have this first buckling mode, which is just this is as n equals 1, or that's our second buckling mode, which is n equals 2, on up and on up. And so we're almost there for what our critical buckling load is. And so we're almost done with sort of the math-heavy portion of the lecture. So just hang with us for just a second. So we need to solve this factor alpha, because remember, we've just let alpha equal this n over e to the I. And really what we want to solve for is this value of n. And it's that value of n is the load at which we will initiate buckling. So we've gone through all of this differential equation work just really to solve for that one value. So rearranging things a bit, we have alpha equals n times pi divided by L. And so if alpha squared equals n over EI, which is just what we just defined that, here arbitrarily in order to get this differential equation to work so that we could use these homogeneous coefficient, constant coefficient solution. And so in doing that, then we have, so if alpha squared equals n over EI, then looking at this one, then n over EI equals little n. And remember, this little n is just sort of the number of half sine waves times pi squared over L squared. So we're almost at our equation for getting state of buckling based upon a critical load. So the buckling load N simply equals, sorry, that's n squared here because it's alpha squared. N squared times pi squared. Kick this EI over to the other side. EI over L squared. So we'll just box that one up. So this is great. We now have a relationship between our buckling. So this is really this is sort of at the onset of buckling, what load causes that. Now I said with a solution, we have all of these various buckling loads, but for Pinpin, it's this first buckling load that we care about. The second one, like I said, would look sort of like a full sine wave, and you can see I can only really get that to happen if I cut down the unbraced length by giving a support here in the middle. And then you can see you've got that nice full sine wave. But if I take that off, well, we're going to go straight to this first buckling mode. And so because of that, we really only care about when n equals 1, because that first buckling mode is going to happen at a much lower load than any of these higher order n's. And once something has buckled, we're not going to then go through these next series of buckling modes, or we're unlikely to for this elastic condition. So it's this first one mode where little n equals 1 that we care about, and that's what our critical buckling load is going to be. So just writing that out formally for the first buckling mode, where this is little n equals 1, we get, and we'll call this the critical load. So this is, think of this NCR is the load at which we initiate buckling. Well, let's just plug in 1 into this n squared here, and we get 1 squared times pi squared times EI over L squared. Well, 1 squared just equals 1, and that gives us our critical buckling formula equals pi squared times EI over L squared. And that is just our Euler buckling formula. Cool. So that's all, pretty nice and straightforward. The math works itself out kind of elegantly if you think about it. I mean, we went from really what was just quite a simple, straightforward free body diagram, and then about a page of mathematics. Now, granted, we did have to know a little bit about differential equations to get the solution, but through some, quite elegant little tricks of substitution, we were able to work out, this equation, which holds quite true for if we have a simply supported member, so we have a Pinpin end, well, then that gives us that, the load at which this half sine wave starts, this buckled shape starts. And so that's great for, if we have this this pin area, and it's going to buckle like that. But what happens if, say, on this end, say that we fix it, but we can still keep a pin here. So, if I grab the element on the back, and, well, you see it sort of now kicks. We've got a slightly, different shape. So we'll show that here on the solid line. I'll grab it here at the bottom. So think of this bottom as like a fixed condition, and the top I'll just buckle. Well, you can see we've got you've got two curvatures here. So you have this sort of S shape versus, if I pin, that goes back to that classic half sine wave. Well, what if I fix both and I move them together? Well, we have yet a different shape. So how do we deal with that? How do we use this critical buckling case in order to describe, conditions other than this, straight, pin condition? So we have the how do we deal with other boundary conditions? So, essentially what we're going to do, and I'm going to gloss over any derivation, but I'm going to draw a series of them here. And what I'll do is I'll draw out these, if we have ourselves our pin, then if we have, say, a cantilever, and then say we have a we'll do our fix that looks something, we'll fix, but it still has to be able to roll down. And I see we have our little ant friend here. He's really excited about Euler buckling, so he's making a small cameo. And then we will have a fixed pinned condition here. So if we draw the deflected shape, our first deflected shape, this is the condition which we just derived. This is this one here. But then if we have this cantilever section, we'll have our load here at the top on each of them. This cantilever, well, what it tends to do is it tends to, really kick over here and sway quite rapidly. The fixed, I just showed you that one. That was, it'll come, and we have sort of these 2 points of contraflexure, and then for our pin fixed, we really have just this 1 point of contraflexure. So if you derive the critical buckling load for this, and we won't do this in this lecture, this is sort of just an overview of Euler buckling in order to get to understand how we apply it when we do our steel design. But if I write down the formula for the critical buckling load for each of these, you'll get NCR equals pi squared EI over L squared. This one will be pi squared EI over 4 L squared, and CR equals 4 pi squared over EI L squared, and this one will be 2.046 pi squared EI over L squared. So, that's somewhat helpful. And this makes sense that we're going to have, the critical load for the cantilever kind of makes sense, and we divide by 4. So it's going to be a much lower. I mean, granted, this is hard for me not to pin it with the second hand here, but it's going to buckle at a much lower load. If we can also see that if we fix both ends, well, that kind of makes sense, where it's going to take a much larger load to buckle that fix condition than that pin condition. And that if we fix one end and we leave the other end pinned, we'll have something in between the two. So, but another thing to note is that all of these shapes still hold the same pi squared over EI L squared. They still hold this half sine function. And so what we want to do is, instead of memorizing, a 4 on the bottom, a 4 on the top, or a 2.046, instead of memorizing that, we want to essentially just modify what this L term is here to go from, the total length L to what we'll call an effective length. So for an example, let's just look at this case here where we've got a fixed pinned. So we'll write down, all buckled shapes. Still sine wave shaped, and then we accommodate different boundary conditions using the concept of effective length. So as I said, let's do an example looking at how we get this effective length, because really what we want is to be able to stick with sort of this one equation and then just modify the length and the section size and the material properties. That's really what we want as a designer. It's nice and simple and straightforward. So in doing that, let's just use this example here of our fixed pinned, and it has our buckled shape that looks like that. So like I said, we want to get everything into a formula which looks something like this. So NCR equals pi squared EI divided by, and we will call this length LE squared. Well, we know our critical buckling load for this fixed pin condition equals 2.046 pi squared EI over L squared. Well, in order to make these two equivalent, we find out that for this condition, LE equals 0.7 L. And so with with that, then we can just plug this in. We get the same critical buckling load, and then all we're doing is we're just modifying the length to deal with these boundary conditions to give us an effective length. So, I mean, if we write down what the LE is here, so we get LE equals 0.7 for our fixed pin. For fixed, I mean, multiplying by 4 is just like having, LE. So this is fixed. We have LE equal 0.5. LE equals 2. Yeah, that's pretty easy to see. 2 squared is LE, so it's basically 2L. So 0.5 L, 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 and then LE equal 1.0 L. And so you can see for each of these different boundary conditions, we just modify what this LE is. And this is quite easy to memorize. Instead of memorizing 4 top, 4 bottom, this in 2.046, we just memorize, well, what does the boundary condition do to our effective length and hence our critical buckling load. So that's quite nice. So we now know how to deal with other boundary conditions. But the other problem that we've looked at so far with this critical buckling load is that it is assumed that every material that we've worked with is initially straight. So we'll bring our little model out here again, and I'll lay it up next to the line here. So if you see next to the line, it's pretty good, but it's got just as ever so slightly, it's a little bit off. It's got just some initial out of straightness. So if we work really hard to line up, we can see we can just if we can just go and get it with a significant buckling load. But for example, if we start with some little bit of out of plane movement, we find, it's actually quite easy to buckle. So once something has started, even with this really small out of plane movement, we can see it's really easy to buckle. Now, why we ask, why is this important for design? Well, that's because real columns aren't straight, and so they have some initial out of straightness. So let's start our notes going again. How to deal with imperfect columns. So, we really have 2 cases which will create these imperfections, if you'll call them. We have a lack of straightness. So, manufacturing tolerance for steel, just for your reference, equals a 1 in 1,000 deviation from straight. So that means that, so a 1 in 1,000 deviation from straight. So say you have a meter long piece of steel. It is still within tolerance. It's still acceptable to be sold if it has 1 millimeter, which is not perfectly down the center line. So, if we had our center line here, and it was a, some this distance long, so say that's, you know, for lack of argument, say that this was a meter long, well, then we could have 1 millimeter to either side, and it's still acceptable. If we make that you know, a 10-meter long section, it means that we can have up to 10 millimeters out of straight. So we have to be able to, you know, contend with that, because, you know, if we look all the way back to our initial free body diagram, well, it's really this deflected shape and the axial load acting on that deflected shape and the eccentricity between that and the support, which causes this buckling moment. And so, you know, if we have some initial out of straightness, well, we're buying material which already has a little bit of this, you know, cooked in, if you would. The other place where this comes into play is from eccentric loading. And so, you know, this is really arising from, you know, detailing of, say, beam column connections. So for an example, so say we have a simple, kind of a simple connection here, where we have a column and it has a beam coming in, but only on one side. And even if that beam is just, say, connected through a web plate, but it has some, you know, some loading on the top. Well, the resultant load is going to come in off center line of our column. And if you think about it, you know, our Euler buckling is all based upon center line of the member. So, I mean, you could draw a member in here. This is the center line. This is what we're looking at, because the center line is where the line of action will be for the internal stress, which is going to be resisting this external force. So what we need to do is we also need to deal with this type of this eccentricity. So this lack of initial straightness, we tend to call this P little delta, and this eccentric loading is P big delta. So these, when we do steel design, will come into a number of things. One is what we'll look at now is really how we deal with some of this P little delta, and P big delta we'll actually cover in a different video where we're looking at second order effects. But so, you know, how do we deal with this? Well, you know, both of these, you know, both generate an additional internal moment. So if we draw our column again, and this is our center line. And that's our load P. And so we'll have some overall deflected shape. But say that we had, you know, our initial deflected shape from, assume, say this is our lack of straightness. This is drawn, quite, exaggerated, but this is our deflected shape before loading. And this is our deflected shape after loading. And if we look at the maximum deflection that we have, well, before loading, we'll call that the deflection here at midspan, we'll call that A. And we'll call this deflection here after loading, we'll call it delta. So say if you solve for midspan deflection, with respect to axial load, this is what you get. You get that this deflection delta, well, it's going to be this little a divided by the critical buckling load, NCR, which, again, reminds you is just this guy here. But it's NCR divided by the applied load N. So instead of P, let's call this N, just for consistency here. Divided by N minus 1. So, and then if we say we plot this up, so, on one axis, let's plot this deflection D with respect to N, and let's just put NCR here. All right, so, if we were to load up N, and so as our value N goes up, well, our deflection's going to go up as well. And what you find is that you get a plot that looks something like this. Where essentially you'll go up, and then as you approach this critical buckling load, your out-of-plane deformation is going to rapidly increase. And that makes sense. So say we start with our little guessed column here. So if this is initially straight, and we'll put some alpha there. And as I buckle, you can see it goes really quick. I'm putting very little load on here, but it goes really quick, and that's this deformation increasing. So if it's nominally straight, push, 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 and then it kicks out. If we have some initial out of straightness, see just this little bit here, I push, and then you can see that it will move rapidly, this out of plane deformation here. So, if we take our little line, and we'll just call, this way is delta. So we'll put our little alpha in here. So say we do, this, so not alpha, this is A. So that's our midspan deflection. And we're putting A distance there. And then I'm going to push. You can see that it goes quite quickly, a lot of out-of-plane deformation. If we start initially straight, we can get a lot more force out of there before it starts to deflect. And that's what this plot is saying. And this plot has a special name. It's called a Southwell plot. Now you might have done an activity which has looked at this before, but there's some interesting things which come out of this as well. So two things which are sort of worth writing down is the midspan deflection. Increases rapidly as n approaches the critical buckling load, which that makes sense, as we're going to buckle soon. The other one is that we never quite reach our critical buckling load. So, that's kind of an interesting thing to ponder. We've done all of this other derivation using this, nice fancy formula. But as soon as we account for just a little bit of imperfection in our column, we realize, well, this is an asymptotic relationship, so it never reaches NCR. And which makes sense, if n equals NCR, we're dividing by 0. That's an undefined equation. So, it means that in real life, as soon as we account for any little bit of out-of-plane imperfection or loading, we know that we won't reach our critical buckling load ever. So we have to sort of modify our Euler buckling relationship when we look at design. So the next thing we need to look at is, so we've only talked about forces, and if we are if we think back to sort of with beams instead of with columns, if we bend something enough, looking at beams. If we bend a beam, and we look at the cross section, well, we will go, if we look at the stress state, we'll go to something less than yield, and eventually it'll get big enough. We'll yield, and eventually we'll get big enough where we'll plastically deform the section. Well, we can't just bend and buckle something for forever. So we have to find out, for buckling, how do we deal with material properties? Yeah, because this, our beam's a nice analogy for this buckled shape. This is instead of beams, we're deforming this moment curvature relationship because of a transverse load, but for an axial load, it's purely just based upon the axial load there. So, looking at that, let's look at material behavior. So, if we're looking at whether we're going to get yielding or not across the section, and if we want to go to essentially a critical buckling stress from a critical buckling load, really what we want to do is sort of get our everything in terms of stress, and we do that, with so if we have an axial load, N, and we have an area A, our stress is just going to be N divided by A. So if the critical buckling load, NCR, equals pi squared times E times I over LE squared, well, to get it to a stress, we just need to divide by the area of the cross section. So we get our critical stress equals NCR divided by A. And then if we expand that out, and instead of putting the A on the bottom, we'll actually just do I divided by A. And we'll see why here in just a second. So we get pi squared times E times I divided by A over LE squared. And so with LE, we could have this as L or LE. We'll say that's equivalent to pi squared E I A over L squared, just for some sort of nicety here. Then if we let this value I over A equal R squared, and remember this is just then what we can do is we can sort of simplify this equation, and we get our critical buckling stress equals pi squared times E divided by L over R squared. And this L over R term has a special name. So L over R equals the slenderness ratio. And it's a measurement of how far, if we think about this, it's really a measurement of how far material is spread out from the centroid, and that's what this R is. So it's sort of how far that material is spread out relative to the length of the material. So that's this I over A. And you think about this as sort of material distance from the centroid, and then we divide that out. We divide the length by that. So just like how we showed the Southwell plot for looking at our relationship between critical stress and our buckling load, well, let's do another sort of generic plot here, because it will be informative of how we use this relationship in order to determine our compression capacity of real members. So in this case, what we're going to look at is steel members. So on the horizontal axis, we'll plot our slenderness ratio, because this is really slenderness ratio. Think about this as our section geometry changes. So this is our independent variable, and we want to look at our dependent variable, which is the stress. So, and in fact, we'll call it our critical stress will be what we plot, and then there will be. So if we plot up this equation, what we get is a line that looks something like that. Obviously, it's smooth in through here. We don't have a discontinuity. But if we look at it this way, Well, this means that if we have a really, really small slenderness ratio, we kind of have infinite buckling stress. So let's say, for an ideal, and the ideal part is important, elastic material, it has infinite buckling capacity. Which is really what this equation's showing. Real materials, though, yield. And so, ideal is what we're here, with this equation, but we're trying to use this for real materials. And so, what's going to happen is if on our stress axis we put in the yield stress of the material and we send that over, well, that means that if we are basically, this area below the graph is what we're looking at. It says that, for depending upon our slenderness, we will either buckle globally or we will squash. And so there will be sort of this delineation of our slenderness ratio where if we're L over R less than this, it's a stocky section, stocky column, and it will fail by squashing. So think about squashing as just yielding in compression, and as our slenderness ratio increases, we get slender columns. And those will fail by buckling. Cool. So now we've got some way to sort of limit this critical bending stress and this slenderness ratio, which helps us, for some arbitrary section which we're picking out, determine, well, what's the failure mode. So we have just one more piece of the equation here before we wrap up, and that is local buckling. And you can think of local buckling as we get these sort of little ripples in the section. So everything that we've looked up to so far has really been about global buckling of the entire system. But then we still needed to modify that global buckling critical stress to then deal with it with a real material. And so once we go to a stress, what we're looking at is, instead of thinking about the section as sort of just a single line, we're now taking into account all of the material properties and geometric properties with that. So the first one is, how close we are to yield of that section. And so this is going to be, our slenderness is, this is a global buckling. And our local buckling is because steel sections are made of thin plates. They have a tendency to buckle. And, this buckling can occur, this sort of local buckling, can occur before the critical stress for global buckling is reached. And so, if this is again something we have to kind of account for. The other thing we need to account for is sort of residual stresses, and residual stresses. Well, decrease. Sigma CR, our critical buckling stress, which makes sense. So if something's cooling and you lock in a bunch of compression on there, and then we're adding more compression, well, it's going to reach this critical point sooner. And so what we'll see over the next few videos is really how the steel standard deals with all of these various permutations and in different, sort of going from a idealized boundary conditions into an Euler buckling. So kind of going from this here into how we deal with additional boundary conditions, and then how we deal with the fact that our members are non-perfect, and so we'll have some initial out of straightness, and so that means we can never get our critical buckling load. And then how we deal with this for a given section by looking at going from really a critical buckling load to a critical buckling stress, so we can design things section by section. And then because it's buckling, though, we still bring in our slenderness as our sort of controlling factor. And then it's these two things, either local buckling or residual stresses, which will further reduce down what our section capacity is. And so we'll step through all of those on these coming videos, and we're starting first with the section capacity where we're looking at this local buckling effect, and then look at sort of a global buckling. So with that, I'd like to thank you for watching.